we want to solve some systems of linear differential equations. Turns out that the best way to do that is to first learn how to solve some systems of linear algebraic equations. If you have linear algebra before, this will all be easy review. Maybe you want to skip through the first part of this video. We're going to keep it very simple, just what we absolutely need. We'll say, suppose we have a system of two linear equations and two unknowns. That's all we'll be concerned with, and the idea is when you take your linear algebra course, you can easily see how to generalize this to more equations and more unknowns. And so we'll always have the same number of equations and unknowns, and it'll only be two. So we just want to introduce some methods, beginning methods for solving systems of differential equations. So we'll use some beginning methods for linear algebraic equations first. One way to solve these is to solve one of these equations for one variable in terms of the other. You can write x1 equals 4 minus x2. You could substitute it in the first equation and get an equation in one variable and solve it. But that becomes very tedious for larger systems. Larger systems, that takes a long time to substitute up through all the equations. What people usually use is the elimination method, and there's a fast form of this that always works called Gaussian elimination, and you learn that in linear algebra class. We're not even going to go that far. We're just going to say, let's learn how to eliminate variables and solve these things simply. Suppose I have these two equations, for instance, and I want to find out what is x1 and x2. Elimination means you can add a mole of one equation to another, eliminate any variable. There's two other operations you're allowed. You can interchange any two equations, and you can multiply any equation through by a non-zero number. So there's three elementary operations you can perform on these things. One, add a multiple of one equation to another, replacing the latter. So you keep two equations at all times. And then you have an equivalent system of equations at all times. Then the second one is to interchange the order of the equations. That doesn't change the solution. Sometimes that's convenient to do just to make things look prettier. And then we said you can multiply an equation by any non-zero number. That's it. These three elementary operations comprise elimination if you use them to eliminate variables. Let's use those to solve this system. So I'll start with this system here. And I want to get rid of x1, say. I could also get rid of x2, it doesn't matter. So I say, if I take minus 2 times the second row and add it to the first row, I'll have minus 2x1 added to 2x1, and I'll get rid of the x1s, right? So let's do that. What do I get? Minus 2 times x1 added to 2x1 is nothing. Minus 2x2 added to minus x2 is minus 3x2. And minus 2 times 4 is minus 8 added to minus 1 is minus 9. I get this equation. And what you do is you add all of one equation to another, replacing that equation, but keeping the other equation. So I'll replace the first equation with this and leave the one that I added the multiple from. Now I've got an equivalent system here to the first one. This has the same solution set, it turns out, as this one. I won't argue the point since this isn't linear algebra class. And so now what can we do? Oh, I could use operation 3 here. I might want to multiply this through by minus 1/3 on both sides. Then the equation will say x2 equals 3, and then I'll keep the second equation the same. Now, once I've got that, I've got one variable solved for, I can just substitute it into the other to find the other variable. So this x1 plus 2 equals 4 tells me that x1 plus 3 is 4, so x1 has to be 1. Maybe before I do that, I could apply my second operation and say, well, this is equivalent to the first system of equations. I could interchange the order and write x1 plus x2 equals 4 and x2 equals 3. I could also do that and get an equivalent system to the first one, interchanging equations 1 and 2. Maybe put a symbol like that or something. Now, then I can put this one up in here and I find that x1 equals 1 and x2 equals 3. So there's a nice easy way to solve these. Turns out that it's even more efficient to put these in matrix form. You won't see a lot of difference for 2 equations and 2 unknowns, but if you start getting 5 equations and 5 unknowns, this notation is much easier. What you have, if you recall last time, is an equivalent matrix formulation of systems of equation. This matrix system, where you write the right-hand side in this vector, the vector variables here, and the coefficients of the variables, 2, minus 1, 1, 1, turns out to be completely equivalent to this one. Why? Because the way matrix multiplication is defined, you take this row, first row, dot product with the first column. First row with first column gives you the first row, first column entry in the result. It says this times this plus this times this equals this. Right? Dot product of this row with this column. This times this plus this times this equals minus 1. Oh, that's the first equation. Then I take the dot product of the second row with the first column to get the second row, first column entry of the result. 1 times x1 plus 1 times x2 equals 4. Oh, that's the same one as here. So you can do that with any system of linear equations. You just put the matrix of coefficients here. You put the variables here in this vector, and you put the right-hand sides here, and this matrix system is completely equivalent to the original system of linear algebra equations, but it takes a little less writing. Right, you only have to write 1 equals, and all these coefficients can go away. And so for larger systems, it makes a bigger difference. Here it's about the same difficulty. But we can do this now, all these elementary equation operations as elementary row operations on the matrix. Because now, suppose I take minus 2 times the first equation and add it to the second over here. That's equivalent to adding minus 2 times the first row of the matrix to the second row of the matrix here, where I'm going to take this and I'm going to reduce the notation even more. Instead of writing all this out, I know x1 and x2 is always here. Let's just put the matrix and augment it with this right-hand side here. And so this is the matrix of coefficients. This is the right-hand side numbers. And if I take minus 2 times the first row, minus 2 times the second row and add it up to the first row, I take minus 2 added 2 is 0. Minus 2 added minus 1 is minus 3. Minus 2 times 4 added minus 1 is minus 9. And look, I get the same equation I did over here, and I keep the same second equation. The elementary equation operations over here are completely equivalent to the same operations on rows over here. Similarly over here, on the second step, when I interchange the order of the equations, well, I can just interchange the order of the rows over here, right? And I get this one. So this is interchanging rows 1 and 2. I'm sorry, I did the wrong one here. That's first I've got to do minus a third times the first row. So this one is minus a third times the first row, replacing the first row. So I'll do an elementary row operation here instead of an elementary equation operation. Instead of multiplying the equation by minus a third, I'll multiply the row by minus a third and get this one. And then I can interchange the rows 1, 1, 4, 0, 1, 3, instead of interchanging the equations. And this system looks just like these equations, right? So by doing the row operations, I can keep in matrix form the same result. Now I can glean from here that x2 must be 3. That's what this last equation says. 0x1 plus 1x2 equals 3. And this one says 1x1 plus 1x2 equals 4, the same as the equation over here. So we can do these in matrix form and solve this system of 2 equations and 2 unknowns. Now, this can be used to find something more exotic called eigenvalues and eigenvectors of a matrix. When I have a matrix, say this one, 2, minus 1, minus 1, 2, there are certain vectors I can multiply it by that don't change their direction when I multiply. For instance, if I multiply this by the vector 1, 1, what do I get? 2 times 1 plus 2 times minus 1 is 1. 2 plus minus 1. And minus 1 times 1 plus 2 is 1. I got the same vector back. Similarly, if I I take this matrix and I multiply it by the vector 1 minus 1. I can take 2 times 1 is 2, plus minus 1 times minus 1 is 3. And then minus 1 times 1 is minus 1, plus 2 times minus 1 makes minus 3 in all. And this vector is 3 times this one. So in each case, when I multiply the matrix times the vector, I got a vector that's the same direction. This one 1 times as long, and this one minus 3 times as long. So we call these eigenvectors. Eigen comes from the German for proper. They're proper vectors. They keep their same direction when you multiply the matrix times them. That's not true of just any vector. And if we want to find the eigenvectors of the matrix, we can solve a system of equations for that, because what that thing says is you have a matrix A, and you multiply it by a vector u, and you get some number times the vector u. That's the basic matrix equation, or maybe I should put these in bold for matrix and vector. But lambda is a number, and so matrix times vector equals number times vector. When you multiply the vector times the matrix, you get a multiple of the same vector. It keeps its direction. That's called an eigenvalue, lambda. And an eigenvector, u. Let's see if we can find the eigenvectors of an equation. Those are tricky. What this really says equivalently is that a u, if I can drop the boldface now just because it's too hard to keep writing it, minus lambda u equals 0. There's an equivalent equation. We just have to remember that u and a are vector and matrix, where lambda is a number, a scalar, we call it. And we can now use a little bit of linear algebra, which again we won't prove, but we'll say it actually has this distributive property that there's an identity matrix, I, where I has 1s all down its diagonal and 0s off the diagonal. It's called the identity matrix because when you multiply by any other 2 by 2 matrix, it gives you the same matrix back. That's like the identity of multiplication of numbers. If you multiply, 1 is the identity of numbers. If you multiply 1 by any other number, you get that other number back. Similarly, if you multiply any matrix times this matrix, you'll get the same matrix back. So it's called the identity matrix. So if I put that in there, it doesn't change anything. I times u is equal to u. It has this property for any vector u. And also you multiply by the matrix A, and IA will always be A. Alright, so with that, with those properties in mind, and again we're not doing linear algebra class, so I'll just wave my hands at the proofs. We have this distributive property I started to say, A minus lambda times the identity, all multiplying u equals 0. One thing you have to be careful about in matrices is you can't necessarily multiply, just switch the order. For instance, you can't, instead of IU, write UI. They aren't compatible for multiplication, right? This is a 2 by 1 and this is a 2 by 2. This one has to have the same number of columns as this has rows, so you can't multiply them. So you can't just multiply in any order, but the other properties of algebra with numbers tend to be true, such as the distributive property. You can say multiplication distributes over addition and subtraction and factor a u out of here. Now what this means is that you have to have, from linear algebra, this is a theorem, in order for this to hold, you need the determinant of A minus lambda, the identity, the matrix, determinant of the matrix, equal to 0. We remember what determinant is, right? So this is true in order that this equation hold when u isn't the 0 So how can we find what that means? That means that we can solve, actually this is a polynomial equation called the characteristic equation. And we can solve this, use this to find the eigenvalues of the matrix. Once we have the eigenvalues lambda, and it turns out that this is always a second degree polynomial equals 0, and you remember from algebra that they'll have exactly two solutions, including any possible multiplicities. So we'll get a lambda 1 and a lambda 2 might be equal. They might actually be complex conjugates, because this amounts to solving using the quadratic formula to solve this equation. But you find these two eigenvalues by this equation, and then once that's done, you can use the original this equation right here, I guess, to find the eigenvectors u. So 2, put this in a two-step method. To find what is called eigenvalues and corresponding eigenvectors of a 2 by 2 matrix A. And remember we said that lambda is called an eigenvalue and u is called a corresponding eigenvector if AU equals lambda u satisfies this equation for, we didn't say maybe clearly, u not equal to 0. Any non-zero vector that satisfies that equation for some number lambda is called an eigenvector. The corresponding number that goes here is called an eigenvalue. So they come in pairs, an eigenvalue with an eigenvector. Just like that last example, we had the vector 1, 1 was an eigenvector with eigenvalue 1, because when you multiply the matrix times the eigenvector, you got 1 times the vector. The other one, the vector 1 minus 1, was an eigenvector with eigenvalue 3, because when you multiplied a by 1 minus 1, you got 3 times the original vector. Alright, so this is what we want, is a vector u, a non-zero vector u, and any number lambda, which could be 0, such that AU equals lambda 0. Here's how we find it. We just solve from these equations. One, we solve determinant A minus lambda I u equals 0. The 0 vector is what this is. Determinant A minus lambda I equals 0, not the 0 vector. For two eigenvalues, lambda 1 and lambda 2. This will always give us a second degree polynomial equation. Then secondly, we'll solve A minus lambda I u equals 0. What's this? Well, this is a matrix, and this is a vector. We're solving a matrix equation like we just did at the beginning. This is why we solve the matrix equation, so we can now solve this kind of thing. This is very fast linear algebra. We're not going to need so much of it. And we solve this for u1 and u2, the corresponding eigenvectors. We just put like that. Alright, so let's try that for our example we had before. Find all of the eigenpairs, eigenvalue with eigenvector, 2 of them, for the matrix A equals 2 minus 1 minus 1, 2 that we had up earlier. How can we find those? minus lambda I equals 0. Well, for lambda, so we write this determinant, let's say a minus lambda I is what? Well, a is 2 minus 1 minus 1, 2. And the identity has ones on the diagonal and zeros elsewhere. And if you multiply by a number, you get lambda, lambda, 0, 0. So there's the 1, 0, 0, 1 matrix with lambda multiplying it. Lambda is some number. And now we want determinant of a minus lambda I equals 0. So we want, and I should put this, comes out to be this. It comes out to be 2 minus lambda, 0, minus 1, 2 minus lambda. So a minus lambda I just amounts to taking the matrix A and subtracting a number lambda off each diagonal element. And so what we want to solve is determinant 2 minus lambda, 0, minus 1, 2 minus lambda equals 0. That's what we want to, oops. This is minus 1. That's what we want to solve. So this, I'm claiming, is always a second degree polynomial equation. Remember, the determinant is this times this diagonal, minus this times this diagonal. So we'll take 2 minus lambda times 2 minus lambda, minus 1 times minus 1 equals 0. We call this the characteristic equation. If you multiply it out, we've got lambda squared minus 4 lambda plus 4 minus 1 is plus 3 equals 0. And this one factors, it factors as lambda minus 3, lambda minus 1 equals 0. And evidently, there's exactly two solutions. Lambda can be 1 and lambda can be 3. Those are the eigenvalues of the matrix. Here's how you solve them. You take the matrix minus lambda on each diagonal element, determinant equals 0. And just solve that easy polynomial equation that results. That gives you the eigenvalues. Now, you want to get the eigenvectors. You solve a minus lambda times the identity u equals 0. This time it's the 0 vector on the right. And how do I solve that? Well, now that I know what lambda is, I can do it for each case. In the first case, lambda 1 equals 1. What do I get? This means subtract 1 times the identity matrix. So I get 2 minus 1, minus 1, minus 1, 2 minus 1. This is the original matrix. Subtracting lambda equals 1 off each diagonal element. And this times u1, u2 has to give us the 0 vector. Oh, it's a system of linear equations. We know how to solve that. We just did that. Let's try it. This is the matrix. 1 minus 1 minus 1, 1 times u1, u2 equals 0, 0. We can write it in the augmented matrix form. 1 minus 1 minus 1, 1, 0, 0. Right? And now we can perform elementary row operations. If we want to eliminate this element here, we could just add 1 times the first row to the second row, replacing the one I'm adding to the second row. So that'll leave the first row the same. Minus 1 times this one added to this one is 0. And then 1 times this added to this is 0. 1 times this added to this is 0. It turns out on these eigenvalue problems, you're always going to get at least 1 0 row down here. And so now what's the system of linear equations? Well, since you only have one equation left and this system is completely equivalent to this one, all you have to do is pick any elements you want, u, such that the first component of u1 plus minus 1 times the second component of u1 is equal to 0. They just have to satisfy this. So any vector, any non-zero vector that satisfies this is an eigenvector. I can choose u1 equal the vector, let's pick an easy one, 1, 1. Alright, because 1 minus 1 is 0. So there's an eigenvector, and then I can pick any non-zero multiple of that. So I found out that an eigenvalue is lambda 1 equals 1. Its corresponding eigenvector is a vector with components 1, 1. Let's write lambda 1 down here. And say, here's one eigenpair. Now I want to find the other eigenvector, the one that goes with lambda 2 equals 3. How do I find that one? Well, it's the same thing. Lambda 2 equals 3. I solve A minus lambda 2 identity u2 equals 0 for u2, where lambda 2 is 3. And let's see, if I take 2 minus 3 minus 1 minus 1, 2 minus 3, subtracting 3 from each diagonal element of the original matrix is what this does. I get this system of linear equations. As before, see, this is now minus 1 and this is now minus 1. This is equivalent to the augmented system, minus 1, minus 1, minus 1, minus 1, 0, 0. This is the same system, just written with a bar here instead of all this stuff in the middle. And now I proceed to apply elementary operations to eliminate variables. Suppose this time I take minus 1 times the first row and add it down to the second one. That'll make this element equal to 0. Then I'll be able to solve the second equation for u2. So I'll take minus 1 times minus 1 added to minus 1 is 0. I'm going to leave the first row the same, by the way. And I'm adding minus 1 times the first row to the second, replacing the second, leaving the first one alone. So minus 1 times that added to that is 0, but also minus 1 times that added to that is 0, minus 1 times this added to this is 0. You always get at least one 0 row out of this. This tells us that the original system is equivalent to this equation, minus u1 minus u2 equals 0, right? That's what this equation says, written out in algebraic form again. So now this equation simply says minus u2 first component minus u2 second component equals 0. So we just have to pick these minus each other. We could pick u2 equal to vector 1 minus 1, just so they're opposite signs, right? This negative each other. So now I have two eigenpairs. I have lambda 1 equals 1 is an eigenvalue corresponding to eigenvector u1 equals 1, 1, or any non-zero multiple of it. And I have lambda 2 equals 3 with corresponding eigenvector u2 is any non-zero multiple of 1 minus